Stator Related Fault Conditions in Electric Motor Analysis, Identifying Issues to Enhance Motor Performance Reliability. Stator Related Fault Conditions, Overview of Stator-Related Faults, Stator Problems, Fundamentals, Common Types of Stator Faults, Stator Eccentricity, Vibration Signature of Stator Faults, Soft Foot, Definition and Types, Effects of Soft Foot on Stator Condition, Corrective Actions and Best Practices, Key Takeaways for Engineers. Representative image illustrating an electric motor stator and its structural relationship to the rotor and frame, highlighting areas susceptible to distortion and electromagnetic force concentration. Stator-related fault conditions are among the most critical issues encountered in electric motor operation because they directly influence electromagnetic performance, mechanical stability, and overall motor reliability. The stator is responsible for generating the rotating magnetic field that drives the rotor, and any defect within the stator structure, windings, or mounting condition can significantly distort this magnetic field. Such distortions often result in abnormal vibration, excessive noise, increased losses, and accelerated wear of both electrical and mechanical components. From an engineering reliability perspective, stator faults are particularly important because they can progress rapidly from minor anomalies into severe failures such as winding burnout or rotor-to-stator contact. In condition monitoring and vibration analysis programs, stator faults are typically classified as electrically induced vibration problems, but they are often influenced or aggravated by mechanical conditions such as poor mounting or soft foot. This presentation focuses on two closely related aspects of stator-related issues: inherent stator problems and soft foot conditions that mechanically distort the stator frame. Understanding the interaction between electrical forces and mechanical constraints is essential for accurate fault diagnosis. By applying vibration analysis, engineers can identify characteristic frequency patterns, directional vibration behavior, and load-related changes that indicate stator involvement. This foundational understanding enables maintenance teams to take corrective actions early, reducing downtime, preventing secondary damage, and improving overall motor life cycle performance in industrial applications. Image showing typical vibration measurement locations on an electric motor, emphasizing radial measurement points used for detecting stator-related vibration characteristics. Stator-related faults encompass a range of electrical and structural problems that originate within the stationary portion of the motor. These faults commonly include stator winding defects, shorted laminations, loose stator cores, and air gap irregularities such as eccentricity. From a reliability engineering standpoint, these faults are significant because they directly affect magnetic flux distribution, which in turn produces unbalanced magnetic forces acting on the rotor and stator structure. In vibration analysis, stator faults often manifest as elevated vibration levels at frequencies related to the electrical supply, most notably at twice the line frequency. For a 50 Hz system, this corresponds to 100 Hz, while for a 60 Hz system it corresponds to 120 Hz. Unlike purely mechanical faults, stator-related vibration may not scale linearly with speed but instead varies with electrical load and voltage conditions. Another important aspect of stator faults is their directional nature, frequently producing higher radial vibration due to magnetic pull across the air gap. Engineers must also recognize that stator faults rarely exist in isolation. Installation issues such as soft foot, base distortion, or pipe strain can mechanically deform the stator frame, indirectly creating or worsening electrical air gap problems. A comprehensive overview of stator faults therefore requires both electrical and mechanical evaluation, combining vibration spectra, time waveform analysis, operating condition assessment, and physical inspection to achieve accurate diagnosis and effective corrective action. Illustration representing magnetic flux distribution within a stator, demonstrating how distortions can lead to unbalanced radial forces and vibration. The fundamental mechanism behind stator problems lies in the interaction between the stator magnetic field and the rotor. Under normal conditions, the stator produces a symmetrical rotating magnetic field that results in smooth torque production and minimal vibration. However, when stator defects are present, this magnetic field becomes distorted, generating unbalanced electromagnetic forces. These forces act primarily in the radial direction and are transmitted to the motor frame and bearings. One of the most important diagnostic fundamentals is the strong association between stator faults and vibration at twice the line frequency. This occurs because magnetic forces are proportional to the square of the magnetic flux, resulting in force components at 2 times the supply frequency. Engineers analyzing vibration data should therefore pay close attention to prominent 2 times line frequency peaks, especially when they are dominant across multiple measurement points. Additionally, stator-related vibration often increases with electrical load rather than rotational speed, which helps distinguish it from mechanical imbalance or misalignment. Understanding these fundamentals allows analysts to avoid misdiagnosis and focus on the root cause of abnormal vibration, particularly in cases where mechanical components appear to be in acceptable condition but vibration levels remain elevated. Example image of stator laminations and windings, highlighting areas where looseness, damage, or shorting may occur. Several common fault types are associated with stator-related problems in electric motors, each with distinct causes and diagnostic indicators. Stator eccentricity occurs when the air gap between the rotor and stator is uneven, leading to localized magnetic attraction and increased radial vibration. Loose stator cores or laminations can result from inadequate fit, thermal cycling, or aging, causing mechanical movement that modulates the magnetic field. Shorted laminations or winding faults reduce magnetic efficiency and increase localized heating, often producing abnormal vibration alongside elevated current and temperature. These faults may coexist and interact, making diagnosis more complex. From a vibration analysis perspective, these conditions often produce similar frequency signatures but may differ in directionality, amplitude stability, and response to load changes. Engineers must therefore integrate vibration data with electrical measurements, thermal observations, and maintenance history to correctly identify the specific stator fault present. Early detection of these common fault types is essential, as continued operation can escalate damage and significantly increase repair costs. Diagrammatic image showing an eccentric air gap between rotor and stator, illustrating how uneven spacing leads to unbalanced magnetic forces. Stator eccentricity is a critical stator-related condition characterized by a non-uniform air gap between the stator and rotor. This condition can be static, where the minimum air gap remains fixed in one position, or dynamic, where the minimum air gap rotates with the rotor. Eccentricity results in uneven magnetic pull, which produces strong radial forces acting on the rotor and stator structure. These forces not only increase vibration but can also lead to bearing overload, increased noise, and in severe cases, rotor-to-stator rub. In vibration analysis, eccentricity is commonly associated with elevated 2 times line frequency components, often with pronounced directionality. The vibration may be significantly higher in one radial direction compared to others, reflecting the location of the minimum air gap. Stator eccentricity can originate from manufacturing tolerances, bearing wear, shaft deflection, or mechanical distortion caused by improper mounting conditions such as soft foot. Addressing eccentricity requires identifying both the electrical symptoms and the underlying mechanical contributors to ensure a lasting corrective solution. Example vibration spectrum highlighting a dominant 2 times line frequency component commonly associated with stator-related faults. The vibration signature of stator faults is a key diagnostic tool for condition monitoring engineers. The most prominent feature is typically a strong peak at twice the electrical line frequency, which stands out clearly in the frequency spectrum. This peak may dominate overall vibration levels and is often present across multiple measurement locations. Another important characteristic is increased radial vibration compared to axial vibration, reflecting the direction of electromagnetic forces acting across the air gap. Additionally, stator-related vibration often shows sensitivity to electrical load, increasing as load increases and decreasing when the motor is unloaded. This behavior helps differentiate stator faults from purely mechanical issues such as imbalance, which are primarily speed-dependent. Time waveform analysis may reveal a relatively smooth but high-amplitude vibration pattern, consistent with electromagnetic excitation rather than impulsive mechanical events. Recognizing these signature features allows analysts to confidently identify stator involvement and avoid unnecessary mechanical interventions. Illustration showing soft foot conditions at motor mounting points, demonstrating how improper contact leads to frame distortion. Soft foot is a mechanical installation condition in which one or more motor feet do not make proper contact with the base or foundation. This results in distortion of the motor frame when the mounting bolts are tightened. Soft foot is typically classified into parallel soft foot, where a foot is uniformly elevated, and angular soft foot, where the foot is twisted relative to the base. Although soft foot is often considered a purely mechanical issue, it has significant implications for stator health. When the motor frame is distorted, the stator core and windings can also be deformed, leading to air gap irregularities and magnetic imbalance. This mechanical distortion can therefore induce or exacerbate stator eccentricity and associated vibration. From a reliability perspective, soft foot is particularly concerning because it is common, often overlooked, and easily correctable if properly identified during installation or alignment procedures. Image demonstrating motor frame distortion due to soft foot and its influence on internal stator alignment. The effects of soft foot on stator condition are both direct and indirect, making it a critical factor in stator-related fault analysis. When a motor with soft foot is bolted down, the resulting frame distortion alters the geometry of the stator core and the uniformity of the air gap. This distortion introduces uneven magnetic forces similar to those caused by inherent stator defects. As a result, vibration levels increase, particularly in the radial direction, and dominant 2x line frequency components may appear or intensify. Over time, the combination of electromagnetic stress and mechanical strain can accelerate insulation degradation, loosen laminations, and increase bearing loads. Soft foot can therefore act as a root cause that triggers a chain of secondary failures if not corrected. Recognizing the link between soft foot and stator vibration is essential for effective root cause analysis and long-term reliability improvement. Photograph illustrating proper motor shimming and mounting practices used to eliminate soft foot conditions. Corrective actions for stator-related faults and soft foot conditions focus on eliminating root causes and restoring proper mechanical and electrical symmetry. For soft foot, best practices include precision shimming to ensure all feet are coplanar, proper bolt tightening sequences, and verification using feeler gauges or laser alignment tools. Pipe strain and external forces should be eliminated to prevent reintroduction of distortion. For stator problems, corrective measures may involve stator core tightening, lamination repair, winding reconditioning, or motor rewinding depending on severity. From a preventive maintenance perspective, ensuring proper installation, alignment, and foundation integrity is one of the most effective ways to avoid stator-related vibration issues. Regular vibration monitoring combined with periodic mechanical inspections allows early detection and timely intervention, reducing the risk of catastrophic motor failure. In summary, stator-related fault conditions are a major contributor to abnormal vibration and reduced reliability in electric motors. These faults are characterized by strong vibration at twice the line frequency, pronounced radial directionality, and sensitivity to electrical load. Stator eccentricity, loose laminations, and winding issues are common electrical contributors, while soft foot is a frequent mechanical root cause that can initiate or worsen stator problems. For engineers and reliability practitioners, the key takeaway is the importance of integrating mechanical installation quality with electrical condition monitoring. Accurate diagnosis requires careful analysis of vibration spectra, operating conditions, and physical mounting integrity. By addressing soft foot and stator issues early, organizations can significantly extend motor life, reduce unplanned downtime, and improve overall asset performance. An engineering-focused, systematic approach to stator fault analysis is therefore essential for effective electric motor reliability management. Summary image reinforcing best practices in motor installation, monitoring, and stator fault prevention.